Now Heisenberg uncertainty principle states that it is impossible to measure both position and momentum of a particle simultaneously with accuracy. Again, I'll repeat again. See, if we have a particle and we need to find the position and momentum of the particle simultaneously, that means we are looking for the you can say correct value of the position and momentum of the particle, and we need to find that value simultaneously. That value, like we want to know the position and momentum of the particle simultaneously. So we get to know that we cannot find the position and momentum of the particle simultaneously with accuracy. That means we can find, but the value is not going to be accurate every time. Like if we do a certain kind of attempt in order to find the correct value of the position, then we will get the correct value of the position, but there won't be a correct accurate value of the momentum. Likewise, if we make an attempt to calculate the accurate value of momentum, we may get the accurate value, but we won't get the accurate value of the position. So that means we cannot measure the position and momentum of the particle simultaneously with the accuracy. That means we cannot find an accurate value for that. So we say that he just wrote this expression in a mathematical way. He said that uncertainty in position, right, into uncertainty in momentum is a constant value. That means the product of uncertainty in position, this is my position, right, and this is my uncertainty in momentum. So my product of uncertainty in position and uncertainty of momentum is a constant value, and it is either equal to or greater than h over 4 pi. So that means it is you can say it is always compulsory that we will get an error in that. That means we will get an error in the product of position and momentum of the particle when we are going to calculate them simultaneously, right. And what will be that error? What will be the uncertainty? That will be something greater than, and one thing you need to keep in mind, that the value is always constant, right. That means uncertainty in position and uncertainty in momentum is always a constant value, right. And the value is constant, but what is actually that value? It is either greater than or equal to h over 4 pi. Means when we will solve h over 4 pi, the uncertainty in position momentum is always going to be greater or equal to actually the value that we get after solving h over 4 pi, where we know that h is a Planck's constant. So this is what we have the Heisenberg uncertainty principle. Now the question must be striking in your mind that what is the reason that we are not able to find the position and momentum of the particle simultaneously. So let me show you that how we are going to find and what are the difficulties we are facing due to the reason we are not getting the correct value. See, this is let's say this is my orbit. Let's say this is our orbit, and in this orbit our electron is here, right. We know that in order to find, and we need to find, I'll write here what we need to find the position and we need to find the momentum of the particle, and the calculation should be simultaneously done. Now what happens, like if we want to know the position, we know that to know the position of any particle or anything, we need to strike a photon over it, or we need to use a light. So what happens when we will use light, the photon will strike this electron, and when it will strike this electron, it will get reflected back, and that reflected light is seen by the microscope, and taking into consideration all parameters, we get to know the position, right. So the similar thing what we are doing. This is the incident light, right, and this is the reflected light, and this is my microscope with which I am going to examine the reflected light. Now what happens, to know the position accurately, if we want to know the position, pinpoint position, we need to use the light of shorter wavelength. We need to use the light of shorter wavelength. And as we know, we have a relation where lambda is inversely proportional to momentum. We know that. So that means the lower is the wavelength, more is going to be the momentum. More is going to be the momentum of that radiation. And as we know, momentum is sum of mass into velocity, and we know that mass always remain constant. So that means it will have the higher velocity, or we can say that it will have the higher momentum. So what happens when this kind of photon just strike this electron, it is able to determine the accurate position, but when it strikes, as it possesses a shorter wavelength and high momentum, it is going to transfer its momentum to this electron. Right, and what will happen when it transfers its momentum to this electron? It will change its trajectory, it will get displaced, and this will be the expected part, that it will move in this position. That means the velocity of the electron just gets changed, or we can say that we are not going to calculate the accurate value of, we won't get the accurate value of the momentum. We have already got the accurate value of the position by using the shorter wavelength, but the shorter wavelength light possesses the higher momentum. So when this kind of radiation or a photon strikes the particle, it transfers its momentum to the electron, and as a result, the trajectory of electron is changed now. So that means we are not able to get the accurate value of the momentum. So that means here our position will be correct, but our momentum is not going to be the correct accurate value. So that means the product of this is the greater constant, and it is either it is greater than or equal to h over 4 pi. Now if we say that we not need to find the momentum accurately, so that means if we need to find the momentum accurately, we need to use light of larger wavelength. Now my wavelength is large, so that means my momentum is going to be small. So this kind of photon is not able to get reflected in a proper way, or we say that it is not able to determine the exact position. So here the error lies in our position. So that means it is almost impossible to measure the position and momentum of the particle simultaneously with accuracy. That means we may find the result, but actually the results won't be an accurate result. So there may be an uncertainty in position, or there might be an uncertainty in momentum. That depends that which kind of light you are using. If you are using light of shorter wavelength, you are going to get inaccurate momentum, because the velocity of electron will get changed in that case. But if you are going to use the larger wavelength light, then you won't get the accurate position. So that means there will exist in the uncertainty in the product of position and momentum. It is definitely going to be, because according to Bohr, he said that he knew that the exact position of electron is this and momentum is this. So this is actually not proved by Bohr, because he was unable to explain this phenomena, right? So this was the second one, the Heisenberg uncertainty principle. And now if we talk about its significance, so again, like de Broglie, we don't come across the electron-like particles in a daily life, that we do not come across the microscopic particles, we come across macroscopic, right? And the macroscopic particles have definite trajectory, even you can calculate the position and momentum of the particular macroscopic object with accuracy, but not in case of the microscopic one, because as I told you that we need to use certain wavelengths of light, and in doing so they are just disturbing the other factor. Like we are going to get the position accurate but not the momentum, and likewise sometimes we will get the momentum but not the position. This is what was the Heisenberg uncertainty principle, and these two principles are the important you can say phenomena that Bohr was unable to explain it.